Hey, how's it going? In this video, I will first I will kind of explain what a ring buffer is, and I will show how to make one. And a ring buffer is basically just a data structure, and it can contain many elements, and it's often used in like low-level firmware. And what I'm trying to do is make a GPU accelerated ring buffer, because normally they are CPU. They're pretty good on the CPU, but using often people use CUDA for ring buffers. Like you can create really fast ones, and it is pretty reliable. They have like a library built for it, and what I'm trying to do is trying to make one for the Mac, because I'm running on a Mac machine and I think it'd be cool to have this. So yeah, so I will make some few header files, and from there we could go. And yeah, so first let me just do a few includes also, my apologies if I'm typing kind of weird. I'm in the dark. Yeah. Yeah. And before I go into kind of like how I'm going to create it, I'll kind of show like the previous things that I worked on. So what test is, it basically has, it creates this device, which is from the Metal device. And what this does is it searches my architecture, and it finds out that I'm running on a ARM silicon. And what I'm trying to do is abstract it to this device pointer, and from there you can do a bunch of cool stuff. For example, you can do really quick matrix multiplication. So this is me setting up kind of a way of multiplying these three buffers really quickly. And when you're iterating through three-dimensional vectors, you would need three-dimensional buffers, and it uses this API that is created by Apple, and it is kind of slept on, to be honest. And I think it could be better. It could be more maintained like CUDA is, because CUDA has everything and it dominates the GPU market. So I just wanted to see if I could try to make a simple library for this Metal. Yeah. So before I go into that, let me first collect let me collect a bunch of headers for it. I don't need a lot of this, but yeah, put it in here. I don't need this kernel. Kernel is just basically like how you're abstracting, like what are you actually doing on the GPU or the CPU. So you can have kernel cores specific. So for example, if you want to do multiplication in a specific way, you can create a matmul kernel and so on. So let's call this GPU ring buffer, and I want this to have a size T capacity, and I want to of size. I could sorry, I haven't done this in a while. And I also want to have I'm going to store the metal device. Dev, and I guess that is kind of, we don't need these because we're not actually using the command queue. We're just creating a device, and then we're going to create a structure around it that basically stores these elements. We could do I guess I could put this in here, and we could shift this up. And I guess we should create a buffer CTX pointer of a, so this is going to be like the main buffer, and we'll call this close enough pointer. So those are all the private elements of this class, and before I go onwards, let me fix that. Yeah, let me just make sure. Yeah, okay, that looks right. And the actual interesting thing is that you can store a lot of different elements in this buffer, and it'll be really quick. And I'll kind of demonstrate how I want to set that up. Sorry, I'm in the dark. So we want to delete this because we don't want any copies. Because if you're copying a ring buffer, that's going to be a huge computational overhead. Basically, copying the entire element and all of the values in it. So if you have like 1,000 elements being like actively doing a lot of computation on it, you're copying each one of those elements in all those threads. And you know, when you have a GPU, it's SIMD, so you have a lot of concurrent things going on. You know, let's not make this a template because we want the class itself to take care of that. Right, okay. So let's do the, I guess what we could pass in is the MTL device pointer, equals device, and we can pass in the capacity, or even 32. What the hell? And I guess we could also pass in, what else could we pass in? I guess for now this is good, because the size will always be, it'll start off at 0. And yeah. Sorry. call metal? Source ring buffer CPP. Okay. So let's start actually making some of this stuff. This is where you ring buffer and MTL. Capacity. And what we're gonna do is we're gonna set so we're gonna make capacity is equal to capacity dev I guess we could do just to make sure. Oh, sorry, it is supposed to be dev. Whoops. Okay, sorry. So first we got to make the buffer. Buffer is equal to new CTX, and this is going to be the size of capacity. And basically for this buffer, we want the device tree to be, so yeah, sweet. All right, what's the deal here? Okay, is it happy now? Okay, very good. And we'll do just delete buffer. Sorry, it's supposed to go here. I always get that wrong. And GPU okay. Okay. So we created a destructor. Now I'll start making some stuff. And by stuff, I mean we need to find a way to actually push this ring buffer. Value and pop. Oh, I guess this could be void. Okay. And you can also make some like other attributes to this class. We could do size t, I guess we could do, sorry, UN32 get capacity, and this could just return capacity. Sorry, this was size T. Okay. And now we can actually create this push function. And We also have the uint32 GPU ring buffer of pop. And we could also do one for printing, because like I want to be able to see this. Would rendering. Yeah. Okay. Print ring. Okay. So let's start actually implementing push. So if the size is equal to capacity, then what we have to do is some specific logic, else we, sorry about that, else we gotta take the size and add. Okay. And yeah. So for the size, if we push to the tail, oh, I forgot the most important part. We need to have a head and tail. Yeah, head and tail. So it just points to the head and tail of the, so, and we push to the tail. Yeah. So what we could do is, so I had this pulled up because I wanted to kind of explain how ring buffers work, and I guess I could just kind of go through it from scratch. And basically, like how a ring buffer works is, let's just say we have a capacity of 3 and a size of 0, because there's no elements in this ring buffer. If we add an element, the capacity still says 3 and the size becomes 1. So on, we add 2, capacity says 3, size becomes 2. And let's say we add a third element. So now the size and the capacity are the same. If we try to push in a 4, where does it overwrite? And if you would ask that, that's a good question. We actually overwrite the oldest element. So in this case, it would be 1. So we keep, so yeah. So when the size is equal to the capacity, we overwrite the head. So in this case, when we push and everything is full, we shift the head by 1. Sorry, I don't know why my keyboard is tripping out. And what we do is we mod it by the capacity. And so it laps. So 4 mod, since it starts at 0, 3 mod 3 overwrites 0 because there's no remainder. So this is the first element. So yeah, it does that. And so else the size increases, and we still need to push the value. So what we do is we go to the buffer, we go to the tail, because we push to the tail, and then we have to get that value. And I forgot to mention the CTX structure should have a value. Okay. It pushes to that value, and now we still have to move the tail. Right, because even the tail also shifts with the head. So that's kind of how push works. Pop is a little bit simpler. And popping just basically means, so let's just say the size is equal to 0. So we have no elements and we're trying to remove. So we're basically trying to access an empty ring buffer. We should throw in a logic error and no pop. And I'm using a logic error because it's not a runtime error, so I guess it's just a logic error. And you gotta save the value, the return value as the buffer, and we had to pass in we're popping from the head, so it's the head value. And what we do is we move the head, so we do the same logic here, right here, and we subtract from the size. Things like this. And we return rect. And I guess we could do for less than. We'll just do a simple we could do buffer of I dot value. We could just print it out like this. And then we could do an end line at the end. Sorry. I think it's like this. Okay. And we've returned everything. And now let's go into test.cpp. And so we've created the device driver here. So we know it knows it's a Mac. GPU ring buffer. We call it ring buffer. Pass in dev. And we'll pass it 3. And then we do ring buffer dot push. And we could do let's do, because normally ring buffers, the first value you put in is how big it is, and then you can push in you just push in random stuff. Ooh, shit. What the hell? Oh, I think I know. Let me look at this. Oh, I know what I'm doing. I'm pushing in a too big of a value. I think. Because I'm doing it. This is just from the make. Duplicate symbol. Oh, is it because I'm adding this? Yeah, I think it's because I'm adding these. Passing in a device and putting let me try to see. Okay. Okay. Oh. I think it's also because in... Okay, I'm not calling any of that. Let me do an object dump, because that will kind of make it clear. Let's do dump st and we do test. Okay. And let's put this into a file called debug.txt. So this was actually a part of the plan. I wanted it to debug. So we need to find the crash. Is it because I'm accessing a different library? I think it might be. Okay. Yeah. I think I understand it now. Yeah. So okay, I'm doing the correct loads. It's loading. Okay, so it's creating the kernel. Okay. Okay. So back to what I was doing. Push 1, 3. B. Okay, let's change these values. Sorry. R4, R5, R6, R7, R7, R8, R8. Okay. Okay. Ooh. Okay. So basically, what it's doing, it's as expected. We only have 3 values, and it properly built it up. So I guess I could say it's complete because now we're storing in values. So now when we do matrix multiplication, it can happen really quickly. So I guess this could be the end of the ring buffer library. And yeah, thanks for watching.